Doctor, we finished. We discussed.
Okay. Okay, so now you guys can start giving me your answers. Okay, so one guy from or one girl from each group can write their answers. What is the answer to statement A, B, C, D, and E? Okay, so write it in the chat, or if you want to open the mic, go ahead. One guy from each group. Go ahead. Give me your answers. One guy or girl. So I had 4 groups, right? 4. Normal distribution, standard deviation, wonder spot, define study. Okay. Okay. That's one of them. Okay. Waiting for the remaining 3. Okay. That's 2. Good. Standard deviation, wonder spot. Any changes?
Doctor?
Yeah.
Okay. Can we say our answers now?
Yeah, sure. Go ahead.
Okay, by the chat or?
You are already
Okay. So A is spot speed, B is normal distribution, C standard deviation, D point or spot, E before and after study.
Okay, great. So I don't know, but you guys seem to be having a hold of everything. Okay, that's good. Okay, yeah, that's good. So spot speed and normal distribution, standard deviation, point to spot, and okay. So your answers are correct. All groups are correct. Well done. Congratulations. Okay, so these questions will not come in the exam, right? Okay, so this is basically like a recap of what we have already done. Okay, it's like a recap of what we have already done. So whatever we have done in this chapter, it was part of the words or part of the statements which I gave you. What we were doing in the end was before and after study, right? Before and after studies, if you make an improvement on the road, then you perform a before and after study to see if your improvement made a significant change in the mean spot speed. And we performed a Z test. Let me go to the slide now. Yeah, so we need to perform a Z test to make sure that our improvement made a change, okay, in the spot speed, the mean spot speed. Okay, so these are the two equations. We already applied it to example as well, and then you take the Z value, look into the Z table, find out its probability. If the probability is 95% or more, we say the change is significant, otherwise it's not significant. Okay, now before performing the Z test, there are two conditions which you have to apply on the before and after data set, and these two conditions we have already talked about earlier as well. The first condition is that both speed samples, the before sample and the after sample, should follow the same distribution. And as you have mentioned in this activity as well, that they follow normal distribution, right? They follow normal distribution. So both should follow normal distribution if you have collected enough samples. Okay. And the second condition is related to collecting enough samples. That is, you should collect at least 30 samples in before and after study, both. Okay, 30 before, at least 30 before, and at least 30 after. So in the last lecture, we talked about the n value, right? The calculating the number of samples using these equations. So somebody uses a very high value of S or very high value of E, and they get a number of samples to be less than 30. Then in that case, it is not recommended to go by the n value. Then you should collect at least 30 samples. Okay, so 30 or n, whichever is higher. So you calculate n, it is more than 30, then you collect n samples. But if it is less than 30, then at least collect 30 samples. And this should be the case for before and after sample both. For before and after sample, at least collect 30 samples. Okay. Now, after you do the first part, okay, that is to know whether we have significant improvement or significant reduction in the spot speed or not. There comes the second question then.
Doctor, sorry to cut you off, but we can't see the slides.
You cannot see the slides. Okay. So the second question is, if the answer to the first question is yes. What was the first question? Do we have a significant difference in the mean spot speeds? Okay, do we have a significant difference in the mean spot speeds before and after the improvement? If the answer is yes, then we go for the second question, which is, did we achieve the required reduction in speed? Second question is, did we achieve the required reduction in speed? So whenever you make any changes in the design of the road, or whenever you put a speed limit, you have a value in your mind, right? You have a value which you want to impose on the drivers. So you made a change in the design. So you made the change using a particular value. So that the change should be helping you to achieve that required value. Similarly, if you put a new speed limit, so you want to achieve that limit, right? You want the drivers to be on that limit or below that limit, right? So you have a value. Whenever you make a change, there's a value in your mind which you want to achieve. Okay. So did we achieve that required value or not? This is the second question. Now this question will only come into the picture if the answer to the first question is yes. Okay. Again, what was the first question? Did we have a significant difference in the mean speeds of the before and after sample? If the answer to this question is no, then the answer to the second question is obviously no. If you did not achieve any significant reduction, any significant difference in the speed, then obviously you cannot achieve your required value, because required value is much lower than the value which you had before, right? So if the answer to the first question is no, there's no significant difference, the answer to the second question is also no, I did not achieve the required value. If the answer to the first question is yes, I achieve the required reduction, I achieve a significant difference in the mean value, then you go for the second question, did I achieve my required value or not? Okay, let us see how we can calculate, how we can make sure that we achieve the required value. This is an example for which we calculated the z value last time. Okay, so in this example, you see the before and after sample. For each sample, you have the mean and the standard deviation and the number of values. We have already calculated the z value for this sample, and you calculated the z value, and then we looked at the probability. It was 98% something. Okay, so the answer, so the decision here is that we achieved a significant difference in the before and after sample. Okay, so the answer to the first question is yes. So I can move on to the second question. Now, the second question is, did I achieve the required value? How much value I wanted to achieve? 60. After putting the new speed limit, this question is about putting a new speed limit. So after putting the new speed limit, I wanted to achieve a value of 60 miles per hour. 60 miles per hour. Okay, obviously after the speed limit. So the after sample should have a mean of 60, right? Or a mean close to 60. Now it is 63. The mean of the after sample is 63. And you are trying to achieve 60. So what should be the answer to the second question now? Yes or no? Did I achieve the required value or not? Yes or no? What do you say? Okay, Jafar says no. Okay, good. I always like the people who are quick to answer. Okay, so you are saying that we did not achieve the required value. The correct answer is, by the way, the correct answer is that I cannot say right now whether I achieved the required value or not. Right now, I cannot say whether I achieved the required value or not. Because why? Because this 63, you are saying on the basis of this 63, right? So this 63 is a sample, is a mean of a sample of vehicles. Maybe if you take another sample, the mean is 60. You don't know. So you cannot take a decision whether you achieve the required value or not on the basis of a sample. You must have an idea about the values of all the drivers. You must have an idea about the values of all the drivers, like the range for all the drivers, in order to make this decision. Okay, so how to calculate the range of values for all the drivers? We talked about confidence interval in the last lecture, and this is what we will use now. The concept of confidence interval. What is confidence interval? It's after applying the central limit theorem to normal distribution, you can find out the range of 95% of the population and 99.7% of the population. If you know these ranges, then you can say, looking at these ranges, that the entire population of drivers has this range of values. So 60 is achieved or not achieved. Then we can say that. Otherwise, just looking at 60 cars, the mean of 60 cars cannot is not like good enough to make this decision. Okay, so we need to calculate the confidence interval for the entire population. Now the central limit theorem, when you apply it, it gives you the confidence interval for the entire population, not just these 60 vehicles. So keep it in mind. Okay, so I need to calculate the confidence interval. For confidence interval, I discussed two ranges, one for 95% level and the other one for 99.7% level. The most commonly used level for confidence interval is 99.7%. 95%. The most commonly used confidence interval is 95%. Okay, so obviously in the question is not mentioned, so I will use 95%. I will use 95%. So let us calculate the confidence interval for this example. Now 95% confidence interval equals to mean plus minus 1.96 E, where E equals S divided by root of N. So S, I'm doing it for the after data, okay, because I'm trying to achieve the required value in the after the new speed limit. So I will use a value for the after data. Standard deviation is 6 and N is 60. So give me the value of E. How much is the value of E here? .775, okay. And then give me the value of the confidence interval. Mean is 63 minus 96.775. Give me the confidence interval now. .481 and 64.519. Okay, so this is the range for 95% of drivers now. And you can see the required value of 60 does not even come in this range. Okay, so now from using this range, I can confidently say how much confident I am now. I'm 95% confident that even if somebody went to the site and like they went to the site even 100 times, there is 95% chance that they will never have a mean value of 60 miles per hour for the speed on that location. Okay, so there is a less than 5% chance, which is obviously it's negligible, right? Less than 5% negligible, very small. So there's a very, very small chance that you may have achieved the 60 miles per hour value. There's 95% chance that you did not achieve. Okay, because you already calculated the range for 95% drivers, and that range does not include the required value. So I am 95% sure, or I will just say my final statement will be that the required value is not achieved. So although I achieved a reduction in the Z value, I achieved a significant reduction in the speed, but it was not up to the required value. Significant reduction, but not up to the required value. Okay. Moving on. Any questions? Is it clear? Do we have any questions? Moving on. I have another example. Okay, so a before and after study was conducted to find out the effectiveness of a series of rumble strips. Okay, before approaching a toll plaza. So toll plaza is like a barrier, a check post where you go and you have to pay before you move ahead. And they wanted to reduce the speed to 40 miles per hour. So you can see the table. The before and after sample is given, mean, standard deviation, number of values for each samples are given here. And we will follow the same procedure. Okay, now what are rumble strips? Rumble strips are they are objects to reduce the speed of the vehicles. Okay, so normally these objects which are used in the rumble strips, they are like this. We call them cat eyes, and you must have seen them with the lane marking. Okay, with the lane marking along the road, you see these objects used very often. But in cases where you want to reduce the speed of the driver, you can use them across the road as well. Okay, so instead of using them along the lane marking, you can use them across the road as well. And sometimes we use also small humps like this, small multiple humps to reduce the speed of the drivers. Okay, so it can be either in this form or this form. Both are like different forms of rumble strips. The main idea is to reduce the speed of the driver before they are reaching somewhere important. Okay, so these are known as rumble strips. So we wanted to reduce the speed of the drivers by these rumble strips to 40 miles per hour, and we have the before and after data. Okay, we will calculate the SY and the Z value like we did for the last example as well. I will calculate the SY value first. So SY equals, for the before sample, I need the standard deviation and sample size 4.8 and 120. So 4.8 square on 120 plus for the after sample 5.3 and 108. This is 5, okay, not S. And 108. Okay, so you're given the value of SY, and then you will give me the value of ZD as well, or Z, which is difference of the mean 43.5. Divided by SY. Okay, so giving the value of SY, then we'll calculate ZD 0.67. Okay. And then you will use 0.67 here. How much is it? ZD. .03. Okay. Now, to decide whether we have a significant difference or not, we will go to the Z table. Okay, and this is why I am doing this example, although it is exactly the same as the previous example, but I am doing it so that I can explain this point to you. Now you see the Z table, these are the Z values, right? The first column and the top row, they represent the Z values. Now you can see the last in this column is 3.4 and it goes up to 0.09. Okay, so the last value of Z in this table is 3.49. Now my value is 4 point something. So 4 is not here. So what should I do if the value which I have for the Z is more than the maximum value of Z in the table? What should I do then? In that case, when you get a Z value which is more than the values given in the table, the Z table, then the probability of that Z value is assumed to be 1. Why? Because the values in this table are cumulative probabilities. So when you go from higher to lower, you will see the probabilities are increasing. You can compare between column to column or row to row. Whenever the Z value increases, the probability is also increasing. So the highest Z value in the table has a probability of 0.9998. This is the highest probability for the highest Z value in the table. Any Z value which is more than 3.49 will have a probability of 1, because after 0.9998, what will you get? 1. And probability or percentage cannot be more than 1. So if you have any value, any Z value which has a value of more than 3.49, because 3.49 is the maximum value in the table, if you have a value which is more than 3.49, so the probability will be 1. The probability of that z value will be 1. So for my example, now I can safely say that I have achieved a probability of 1. Okay, so if you have achieved a probability of 1, then my decision is that the changes or the difference is significant. Okay, because my limit was for the probability was 95%. So if the probability is 95% or higher, I will say the change is significant. In this case, it is 1. So obviously the change is significant. Okay. The remaining part of this problem is the same what we have done today. You have to calculate the 95% confidence interval. So you calculate the E value and you will calculate the 95% confidence interval, and then you will answer whether you have achieved the required value of 40 miles per hour or not. Okay. So we have already answered the first question. Yes, there is a significant change in the before and after study. Now you will answer the second question, which is, did you achieve the 40 miles per hour speed limit or not, the required value or not? Okay. So I believe you can do it yourself. I will not go into that. You have to calculate the E value and then you will calculate the confidence interval like you did today. I'll move on to the second or another analysis related to spot speed, which is the check for normalcy. We call it the chi-square test. Chi-square test. When I was discussing, or when I started the discussion of normal distribution, I said spot speed data follows follows normal distribution. Why? Because the shape of frequency distribution curve was a bell shape. Okay. So depending upon the shape of the curve, I was saying the speed data follows normal distribution. Chi-square test is a mathematical proof that the speed data follows normal distribution or not. Okay, so in some cases, plotting the graph may not be possible, or plotting the graph may be confusing you. Okay, so in that case, you can, or you want to double check it, then you can do a chi-square test, which is a mathematical test to prove whether your spot speed data follows normal distribution or not. So you can see chi-square written here. Now I pronounce it chi, not chai, because I love chai. I drink chai. Okay, so I don't want to. I don't want to give them. I don't want to merge them. Okay, so chai is separate, chi is separate. Okay, for my sake, say chi-square. Don't say chai-square. Okay, for performing the chi-square test, I need the chi-square value. Okay, how to calculate the chi-square value? You can see the equation here. For each group, now you should remember that speed data was divided into speed groups. Okay, it was divided into speed groups. For each speed group, I had the number of values and so on. So for each speed group, you will calculate this ratio. What is this ratio? N minus f square upon f. What is n? Number of observations in each group that we already took from the field. We already gathered that n data from the field. Then f is what we call as theoretical frequency. Theoretical frequency. The number of values which should be in a group if the data is following normal distribution. The number of values which should be in a group if the data is following normal distribution. Okay, so this is what we call as f. So you will calculate this ratio for each group and then you will add it for all the groups. Summation for all the groups. And in the end, you will have the final chi-square value, the total chi-square value, and I will show you in an example what to do with the chi-square value. Okay, but first of all, let us see how we can calculate the chi-square value for each group. So before calculating the chi-square value, I have to perform some transformation and calculations. I cannot directly calculate the chi-square value because first of all, I don't know the f value. N is coming from the field, but I don't know the f value. Okay, before you go on to the calculation of chi-square, you have to do some changes in the data. The data set which we have used for plotting frequency distribution, cumulative frequency distribution, calculating mean and standard deviation was this data set. Okay, now what is in this data set? You have the speed groups and they are in ascending order. So the lowest group is at the top The highest one is at the bottom. The first group has 0 values. The last group has 0 values. Okay, and for the first group and the last group is 0. Now I need to transform them to calculate to perform the chi-square test. I need to make some changes in the data. So pay attention. What are the changes? The first change is the groups which were having 0 values, they are now taken out. So you don't see any group at the start and any group at the bottom which has 0 values. And I told you at that time as well, the 0 values, these groups are inserted so that we can have a closed form of the frequency distribution curve. So those groups were actually not observed. The speeds in those groups were not observed in the field. There was 0 observation in those groups, right? So I inserted these groups so that the frequency distribution curve is closed. Ends at 0, starts at 0. Now for the chi-square test, I will remove these groups. Okay, so no group at the start or at the end has 0 observation. Okay, so the groups with 0 observations at the start and end are removed. First change. Second change, look at the order of the speeds, the speed groups. The order is now descending. The order is now descending. Okay, there it was ascending, now it is descending. This is a second change. Okay, so you will rearrange the speed groups into descending order, and the frequencies will be also reverse for each speed group. Okay, so 2 was the actual frequency for the highest speed group. Okay, so when you are reordering the speed groups, you have to reorder the frequencies as well. Okay, frequencies are with the groups, they will change with the group. Okay, second change, groups are now arranged or ordered in descending order, the highest at the top, the lowest at the bottom. Now you see the upper limit of the first group and lower limit of the last group. Upper limit of the first group infinity, lower limit of the last group minus infinity. Third change. Okay, so 3 changes. I will say it again. First change, the 0 group, the 0 values group at the start and end removed. Second change, groups arranged in descending order. Third change, the first group, the highest group, upper limit of infinity, and for the lowest group, lower limit is minus infinity. Okay, so the highest upper limit is infinity, the lowest lower limit is minus infinity. So 3 changes will be made. And as I said, n values should be rearranged when you are rearranging the group with the respective groups. Now for each group, what you will do, you will take the upper limit. You will take the upper limit, okay, and you will convert it to its equivalent z value. So the fourth column is for the z value. How to calculate the z value? I have this equation. Okay, this equation says z equals x minus mu upon sigma. What is x? The values from the upper limit column. What is mu? The mean of the data. We already calculated the mean for this data set. This is the same data set from which we started our chapter. Okay, so mu is already with us. We have already calculated it. What is sigma? Standard deviation. Sigma is standard deviation. Okay, so for this data set, I know the mean and the mu, and x value will change for each group. Now the first value, the first group, remember I changed the upper limit to infinity. So infinity minus anything plus anything will remain infinity. So for the first group, the z value is always infinity because the upper limit is infinity. Okay, for the first group, just put infinity as it is. Okay. Second group, how did I get 2.57? Let me show it here. Okay, so z value, x, the upper limit 64. 64 minus mean. This is the mean 48.2. By standard deviation. This is standard deviation 6.06. So this should give you 2.57. You are looking at here. For the next group, 64 will change to 62, and then 60, and then 58. Mean and standard deviation will not change. Mean and standard deviation are the same for all the groups because this is for the entire data set. Now, since you have the z value, for each z value, go to the z table and find out its probability. Go to the z table, find out its cumulative probability. Okay, so the first value is infinity. Obviously, the table does not have a value of infinity. And I already told you today, if the value which you are having for z is more than the value in the table, then you take the probability to be 1. So again, for the first group, I don't have to look at the z table. For infinity, the probability is 1, the highest value. Okay, because infinity is not in the table. Any value which is not in the table and it's higher than the values in the table, the probability is 1. So for the first group, the probability is 1. For second value, 2.57. I go to the table just to refresh your mind. 2.5 is here and 0.07 from the top row. Okay, so 2.5 from here and 0.07 from here. So the probability is 0.9949. 0.9949. So you see 0.99, where is it? 0.9949 for 2.57. Then do the same thing for 2.25, 1.92 and so on. Okay. Now you see some z values are negative as well. Again, there are no negative values in the z table. The z table does not have any negative values. Now what should I do in that case? For example, you want the probability for minus 0.03. For minus 0.03. Now first of all, this table, the z table which is in the slide or in the book, is only half of the actual z table. The actual z table has negative and positive values both. The actual z table has negative and positive values both. Okay, but how to use this table, the half table, for the negative values? It's simple. Find out the probability without the sign. So you will find out the probability of 0.03, just 0.03, which is this one, 0.0 and then 0.03. So 0.5120. So probability of 0.03 is 0.5120. Now how do I calculate the probability of minus 0.03? I'll take the probability of plus and I will subtract it from 1. Okay, so the probability of 0.03 is 0.5120. So 1 minus 0.5120. Okay, this will give you 0.4980. Okay, so this is the probability of minus 0.03. So whenever you are looking for a negative z value, the probability of a negative z value, this is not given in the table. So what you do, you take the and if obviously I'm talking about half table. Okay, the table which you are having in the book, which does not have negative values. So you go to that table, find out the probability without the sign, and then whatever probability you got, you do 1 minus that value. This will give you the value for the probability of the negative value. Okay, so if you want it for example, now for minus 0.36, get the probability of plus 0.36 from the table, and then 1 minus that probability will give you the probability for minus 0.36. Okay, so for each z value, find out the probability from the table. These are cumulative probabilities. Using them, I will calculate the probability for each group. Okay, so how to find out the probability of each group from the cumulative? You do the subtraction, take the difference. So 1 minus 0.9949 will give you the probability of the first group. Then 0.9949 minus 0.9878 will give you 0.0071, the probability of the second group. So for each group, you will take the difference of the cumulative values for the two groups. Okay, these are the probabilities for each group then. Now these probabilities will be multiplied with total number of values in the group. Total number of values in the group. This particular data set has 368 values. You can count it from here. Do the summation of all the values for all the groups, and you will get the total number. So in this case, we already know, we have already done it. That is 368. So each of the value, each of the probability of the group will be multiplied by 368. And this will give you the f value, okay. So 0.0051 multiplied by 368 will give you 1.8768. 0.0071 multiplied by 368 will give you 2.6128, and so on. So all these values will multiply by 368. So you got the f now. You get the f value. Now if you look at the chi-square equation, I needed n, which I already have from the field, and I needed f. So f is just calculated. Right now I just calculated f. So I should be able to calculate chi-square, but I need to perform a check on the f values. What is the check? No f value should be less than 5. No f value should be less than 5. Now what will happen if it is less than 5? You merge it with the next group. Okay, whatever group, whatever immediate group you have, you will merge the group which has f value less than 5. So for example, if you look at the first two groups, both of them have value less than 5. So 1.87 will be added to 2.61. Now if you add them, the value will still not be more than 5. The value will still not go to 5. Okay, so I will merge it with the third group then. So merging will continue until the final value of f becomes more than 5 or 5. 5 is also acceptable. Okay, so I merge the first two groups, the value is still less than 5, I merge the third group. Okay, for the remaining groups it's already more than 5, so I don't have to merge it. But the last two groups, again the same problem. The last group 3.8 and 4.74 less than 5, so I have to merge them. Now if you merge 3.8 and 4.7, it becomes more than 5, so I don't have to merge with any other group now. Okay, so you merge them, you get 8.57. Okay, but in the case of the first three groups, I had to merge the three groups to make it more than 5. If you just, when you were just merging the two groups, it was not more than 5. Okay, so you merge the any f value which is less than 5, you merge it with the immediate group. And if after merging the f value becomes 5 or more, you stop like you did for the last two groups. If it doesn't become 5 or more, you merge it with the third group, and the merging will continue until the f value becomes 5 or more. So in the case of the top groups, I had to merge 3. In the case of the bottom groups, I had to merge 2. So every time you merge, you have to look at the value. What is the value? Okay, and 5 is our limit. Okay, so you can see the combined value of f for the first three groups. The remaining are what you have already calculated, and the combined value of the last two groups. When you are combining the f values, you need to combine the n values as well. So how did I get 12 here? I merged the three groups, right? So 2 plus 3 plus 7 is 12. And then again, how did I get 10 here? I merged two groups, right? So for two groups, 5 plus 5, 10. Okay, so now you will use the n and f values of the merged groups. Okay, so how to calculate the chi-square? So how do I calculate the chi-square here? This is the equation. This is the sample for the first group. Okay, the first set of groups, the merged groups. So f is 10.08, n is 12. So 10.08 minus 12 square divided by f value, which is 10.08. So this will give you the chi-square for the first group. So in the same way, you will calculate the chi-square for each group, and then you will do the summation for all the groups. So this is the last value, 11.6669 is the combined chi-square value for this entire data set. Combined chi-square value for this entire data set. Now I wanted to continue to finish this example, but obviously we are over time, so I cannot finish it. So what I will do, I will make a small video just for chi-square and upload it. Okay, so that you guys have a complete procedure, and after the vacation we will discuss it as well. Okay, because obviously there will be a break, and if I try to do it after the break, I have to start from the scratch. So we will discuss it. You will see the video. We'll discuss it inshallah after the break. Just to keep the continuity, I will upload the video. Okay, any questions what we have done up till now? Any questions, suggestions, anything?
Doctor?
Yeah.
I would appreciate if you call my name Muhammad. It's not Jafar.
Okay.
Okay.
Right.
That's fine.
Yeah. As like it's the convention in Pakistan. You know, everybody puts the first name as Muhammad. Okay. But sorry, yeah, I know that, but the habit. Okay. Any other problems with me? Any other guy or girl who has a problem with me? You can tell me these things as well. Yeah. Okay. When I say any questions, I don't only mean the questions related to the course. If you have something which is bothering you in my style of teaching or the way I address you can let me know. I don't mind. Any questions, any queries? Everything is clear? Okay, so when I upload the video, please have a look at it and have a nice vacation. Okay, I hope, and don't forget that you have to submit the project part after the vacation. So look at the guidelines, look at the second lecture video. Okay, and have a nice vacation. See you inshallah after the vacation. And thank you for listening. Thank you for participating. See you after the vacation. Assalamu alaikum.